Last time I proved that useful lemma for proving that Lie algebras are semi-simple. It applied in particular to the Lie algebra SLN and to the symplectic Lie algebra and to the special orthogonal Lie algebra. So it showed that all of those are semi-simple Lie algebras. I guess we really didn't need the lemma for SLN. It's very easy to show that the Lie algebra SLN is actually a simple Lie algebra right away. It was pointed out to me that I've been misusing the word simple. Every time I say simple, you should always read non-abelian. Simple. I just really can't get over the fact that the one-dimensional Lie algebra counts as a simple Lie algebra. So I've been misusing the word simple for Lie algebras and for algebraic groups all the time. When I say simple, I mean non-abelian simple, and then I've not told any lies in the previous lectures. Okay, so this lemma is good. It lets us prove that the symplectic and the special orthogonal, those classical Lie algebras, are semi-simple Lie algebras. We don't yet know that they're actually simple Lie algebras. Okay, so yes, these infinite families of classical Lie algebras. I guess I should write down what n is here. SLN starts with SL2. That's the first in the SL family. Symplectic starts with SP2, that's the first in the SP family, and the special orthogonal starts with n equals 3, so SO3, that's the first in the special orthogonal family of classical Lie algebras. And you might notice that actually the first one in each of these families happen to be isomorphic to each other. They are all the three-dimensional simple Lie algebra. Okay, so we have examples of semi-simple Lie algebras, SL, SP, and SO, which you should maybe care about already. So it's kind of reasonable to be studying this class of semi-simple Lie algebras since it contains these infinite families which are very important. So that useful lemma from last time, that was a very easy way to prove that some given Lie algebra is semi-simple. There's another important criterion for semi-simplicity, which I want to talk about today. Honestly, it's not as practical to use this criterion to prove that some given Lie algebra is semi-simple, but it's going to be very important theoretically. So this criterion involves something called the killing form. The killing form on a finite dimensional Lie algebra G is the bilinear form kappa for killing, so on a pair of elements x and y of G, I need to get a scalar out. Okay, so this kappa goes from G cross G to the field, bilinear form. And to define it, you look at add x and you look at add y. So I'm using the adjoint representation here. That's a Lie algebra homomorphism from G to the general linear Lie algebra GL of G. And you remember add x of y was just the Lie bracket xy. So you take add x and you take add y. They're both linear maps from G to G. You compose them as linear maps, and then you take the trace of that endomorphism of the vector space G. That's the killing form. So let's see. Let's work out a few properties of the killing form. Kappa of xy equals kappa of yx. So that's saying that it's a symmetric bilinear form. That's pretty obvious because, well, remember for square matrices A and B, trace of AB is trace of BA, and that's all that's going on there. More interesting is that kappa of bracket xy z is equal to kappa of x bracket yz. So this is often called the associative property. And maybe that needs a little bit of a proof, so let's see if we can do that. Remember, add is a Lie algebra homomorphism. So add of the bracket xy is the commutator of add x and add y. So I can just write the left-hand side of this equation. It's just the trace of add x composed with add y composed with add z minus add y composed with add x composed with add z. And the right hand side similarly is the trace of add x, and then I need to take the commutator of add y add z. So that's going to be add z add y. And so we need to check that these are the same. Well, that's the same matrix on both sides. But here I've got to do one little trick. Oh yeah, all I have to do is move that add y to the right using trace of AB as trace of BA. So these are equal. And so there we go. That's an easy enough little check. Equivalently, saying that the killing form is associative can be written as saying that kappa of add y of x with z is the same as kappa, not equal, plus kappa of x add y of z. That sum is 0, which says that the adjoint action of G on itself leaves the killing form kappa invariant. We've talked about what it means for a Lie algebra to leave a bilinear form on some G module invariant. It's exactly this equation. In fact, I prefer not to use the word associative for this property. I actually prefer just to use the word invariant. So the killing form on a finite dimensional Lie algebra G, it's a symmetric invariant bilinear form. Invariance is important because the invariance implies that the radical of the killing form, remember, the radical of a bilinear form on a vector space, it's all the vectors in the vector space whose inner product with everything else is 0. The radical of the killing form is an ideal of the Lie algebra G. Okay, so you can easily check that invariance property implies in particular that the radical of the form is an ideal. So let's just look at a quick example. Let's do SL2. So for SL2, we have our usual basis. We've played with this before, and we know what add E looks like. It's a three-dimensional Lie algebra. So add E is going to be a 3 by 3 matrix in this basis EHF. Add E of E is 0. HE is 2E, so add E of H is minus 2E, and the bracket of E and F is H. Okay, so that's the matrix for add E, and I think the matrix for add F similarly works out to this guy, 0, 0, 2, 0, 0, 0. And so now you can calculate the killing form EF. So that's just going to be the trace of this product of these two matrices. So I've actually got to multiply 3 by 3 matrices together, but it's not too bad. 2, 0, 0, 0, 0. So the killing form EF is just 4. I guess you could do H as well. Add H is this matrix, HE is 2E, H commutes with H, and HF is minus 2F. So the killing form of H with itself, that's just going to be the trace of that matrix squared, which is 8. So, you know, with simple calculations like this, you can work out the gram matrix of the killing form. In this case, so in our ordered basis, EHF, the gram matrix of this bilinear form, we just worked out the EF entry was 4. It's a symmetric matrix, and the HH entry is 8, and it turns out those are the only non-zero entries in that gram matrix. In particular, the determinant's non-zero, so it's a non-degenerate bilinear form. But that's just SL2, right? It's three-dimensional. It's not too bad. I can work out these 3x3 matrices. But even if you try and do SLN for n bigger than 2, the Lie algebra's dimension is n squared minus 1. And so this adjoint representation is rather big. You're going to have to work with n squared minus 1 by n squared minus 1 matrices. And it's really going to be rather painful to calculate this killing form explicitly in pretty much any other example that we care about. There's another way to go. There's another less painful way to get a bilinear form. Let's just look about maybe SLN for bigger n than 2. So this is called the trace form, tau. So this is another bilinear form on the Lie algebra SLN. Actually, all you really need is a linear Lie algebra. And by definition, tau of xy, the trace form, it's just, well, you just take x and y, they're n by n matrices, you just multiply them as n by n matrices, and then you compute the trace. So really what's going on here is that we're using the natural representation of G on the vector space V equals C to the n, right? SLN, it's already given as a Lie algebra of n by n matrices, and so I'm just taking the trace of these endomorphisms x and y on the vector space V. This is just a composition of endomorphisms of V. So I'm just using this in place of the adjoint representation. The killing form is defined by the adjoint representation. So this is much easier to calculate because you don't have to work with n squared minus 1 by n squared minus 1 matrices. You just need n by n matrices, and that I think I can do. For example, if you took this matrix in SLN, I need what if I just put 1 and minus 1 as the first two entries, and there's our n by n matrix. Then the trace form, H with H, it's just the trace of that matrix squared, and it's just 2. Okay, much less painful because we've got a much smaller representation, this natural representation dimension n, rather than the adjoint representation, which is rather large. Again, the trace form is symmetric, well, because it's a trace, and it's an invariant bilinear form. That associativity property still holds. So its radical, the radical of the trace form, is an ideal of our Lie algebra G equals SLN. But now if you use the SLN is simple, the only ideals are 0 or everything. And I've just checked that this form isn't identically 0. So the radical is not everything. So actually the radical of the trace form has to be 0, i.e. the trace form is non-degenerate on the special linear Lie algebra SLN. And so this is good for me because if I want to go back to the killing form now, I claim that the killing form on SLN is just a scalar multiple of the trace form for some scalar. Let me see if I can explain that to you, and you'll see right away this is actually rather a general argument. I'm doing it for SLN, but actually it shows that on any simple Lie algebra, any two invariant bilinear forms are just multiples of each other. Any two non-zero invariant bilinear forms are just multiples of each other. So let's see if I can prove it in this SLN case. So what I'm going to do is I'm going to consider the bilinear form t tau minus kappa. Let's let G sub t be its gram matrix in some basis. So this is just T times the gram matrix of the trace form minus the gram matrix of the killing form. So the determinant of that gram matrix is this is a dim G by dim G matrix. I'm timesing every entry by T. So when you take determinant, you're going to get what? T to the dimension of G squared times the determinant of G tau, and then you're going to get lower powers of T. And that determinant of the trace form was non-zero because we checked that the trace form was non-degenerate already. So this is not the zero polynomial. So now you can just pick T to be a root of this polynomial. So that's picked my value of my scalar T. And so then this gram matrix has determinant 0, which means that this form, T tau minus kappa, is actually degenerate. But it's an invariant bilinear form. Since it's invariant, its radical is an ideal, but we're dealing with a simple Lie algebra. So once its radical is not 0, it must be everything. So actually it must be identically 0. But if this form is identically 0, this shows that kappa is T tau, as I claimed. Okay, so it's just a little illustration, but it's a rather general argument. And if you actually wanted to know the killing form exactly now, you would just have to find the scalar T. And you could do that by actually just calculating the killing form, kappa of h comma h, with just one nasty calculation to find out what the scalar is. But even that I really don't want to do. All that's important for us is that there's a scalar there, and that scalar is non-zero. So the killing form is also non-degenerate on SLN in general. You really never need to know anything more about that scalar than that. So you avoid calculating the killing form explicitly after this. Just work with the trace form. Why do I know that that scalar is non-zero? Well, that's the next theorem. So G here is any finite dimensional Lie algebra. Of course, we're working over the complex numbers. That's assumed always. And the theorem says that G is semi-simple if and only if the killing form on G is non-degenerate. So I want to prove this, I think I'm going to kind of half prove it today, because there's a ingredient we need in the proof that's a little bit more difficult. So the proof depends on another result, which is Cartan's criterion for solvability. So I'm going to state Cartan's criterion, and then I'm going to prove this theorem assuming Cartan's criterion. But the proof of Cartan's criterion is going to have to wait until next time, because it's a little bit technical. So here's the criterion. It says that if you have some linear Lie algebra, so a subalgebra of GLV for V finite dimensional, and if the trace form is 0 for all x and y in G, right? So we're dealing with a linear Lie algebra. So the trace form, it just means think of x and y as endomorphisms of V. Tau of xy is just the trace of x composed with y. So suppose the trace form is just identically 0 on this linear Lie algebra. The conclusion is that G is solvable. So let's put a box around that. That's going to be proved next time. So assuming this, let's prove the current theorem. So let me see. I'm going to prove that G is semisimple if and only if kappa is non-degenerate. So let's let n be the radical of kappa. So we've observed that that's an ideal of our Lie algebra G. So that's the radical of the killing form. So so it's an if and only if. So let's suppose first of all that G is semisimple, and show that n is 0. Well, as G is semisimple, the center of G is 0. So that means that this adjoint representation from G to GL of G is injective. Remember, the kernel of ad is the center. Now what I'm going to do is I'm going to apply this Cartan criterion to this subalgebra N. So I'm working in the adjoint representation. So G embeds into GLG. So I'm just going to think about this N, the radical of the killing form, as being just a subalgebra of GL of G via this embedding. Okay, so now I'm just working inside GL of G, and so the tau in Cartan's criterion, it exactly is this killing form kappa, right? So tau equals kappa, and n is the radical of kappa. So I'm applying Cartan's criterion to the Lie algebra n sitting inside GLG, and the killing form being 0 tells us this tau xy is 0 for all x and y in G, tau being the trace form on GLG coming from this adjoint representation. So we do this, and we get that n is solvable, but we're assuming that G is semi-simple, which means that it has no non-zero solvable ideals. So this means that actually n is 0, and that does the job. So the killing form is non-degenerate. Conversely, let's assume that the radical of the killing form is 0, and we must show that G is semi-simple. Okay, so let's let B be, well, let's assume it's got some non-zero solvable ideal, and we'll try to get a contradiction. out of that. Okay, so I've got some non-zero solvable ideal B of G. Let's let A be the last non-zero term in the derived series of B. So then this A is non-zero. It's an ideal of G. And if the derived subalgebra of A is actually 0, because A was the last non-zero term. So this A is actually an abelian Lie algebra. Now I'm going to take some x in this A and y in G, and I'm going to consider add x, add y, add x, add y. So that, where does that go? That goes from G to G. That's the add y, and then I'm taking the bracket with x in A, but A is an ideal. So when I do add x, that takes me into A, and then I'm doing add y, which takes me still into A because A is an ideal, and then finally I'm doing add x again, but A is abelian, so that time it gives me 0. So this is 0. This shows that add x, add y squared is 0. So add x composed with add y is nilpotent. And if you're nilpotent, well, all your eigenvalues are 0. So the trace of add x, add y is 0, i.e. the killing form kappa of xy is 0. And this shows, since this was for every y in G, this shows that A lies in the radical of the killing form, n, but n is 0, and so that's a contradiction because our A was non-zero. Okay, so that was kind of the easy parts of the proof, and we've pushed all the actual work to proving this theorem onto Cartan's criterion, which I have not yet proved. So next time we're going to have to prove Cartan's criterion, and then we'll be done. This is kind of what we're really after in the end. Lie algebra is semi-simple if and only if its killing form is non-degenerate. Okay, so we've now got to sort of start getting ready to prove Cartan's criterion. So this feels like a bit of a digression is about to come. I'm preparing for the proof of Cartan's criterion next time. So the digression is to discuss some linear algebra. And the linear algebra is called the Jordan decomposition. So this is the following theorem. Let V be a finite dimensional vector space over the complex numbers. Well, that's where we're working, right? But actually any algebraically closed field would be okay for this. This is a general result. And let's take X to some endomorphism of V. And the theorem says, the Jordan decomposition says that there exists unique endomorphisms xs and xn in NC of V, such that, well, xs is semi-simple. I'm not sure I've used that word before. That's the word used, but it just means the same thing as diagonalizable. So it means that the minimal polynomial of xs has distinct linear factors. Xn is nilpotent, so some power of xn is 0. We've certainly used that a bunch when we were talking about nilpotent Lie algebras and Engel's theorem. Thirdly, x is xs plus xn. So this xs and the xn sum to x, and finally xs and xn commute. Xs is called the semi-simple part of x. Xn is the nilpotent part. So it's important that they are unique, and you need all of these properties in order to get the uniqueness part of this theorem. Moreover, there are polynomials P of t and Q of t in some indeterminate t with constant term 0 such that xs is just the polynomial P of t evaluated at x, and xn is Q evaluated at x, right? So the semi-simple and nilpotent parts of x, they are both just some polynomials in x for polynomials with constant term 0. Okay, so let's prove this, and then I'll just give you a little bit of discussion about the importance of Jordan decomposition, and then I guess the first thing we'll do with it next time is we'll use it to prove Cartan's criterion for solvability. But in fact, this Jordan decomposition is going to carry us through the whole week. It's quite an important topic. Let me maybe do the uniqueness. That's a little bit easier. So suppose xs and xn are as in the theorem. And I mean the whole theorem, including this last part. So I'm going to establish that when I prove existence. And let xs prime, xn prime be more elements, more endomorphisms satisfying 1 through 4. Okay, so that means that x is xs plus xn and s prime plus xn prime. So xs minus xs prime equals xn prime minus xn. Now I'm going to observe that as xs is some polynomial in x, and xs prime commutes with x by properties 3 and 4, xs prime commutes with xs. Similarly, xn prime commutes with xn. Now, if you have two commuting diagonalizable matrices, you can simultaneously diagonalize them. Okay, so xs and xs prime, they're simultaneously diagonalizable, so that means that the difference xs minus xs prime is itself diagonalizable. So xs minus xs prime is semi-simple. Remember, that just means diagonalizable. And similarly, xn prime minus xn is nilpotent. Right, each of them is nilpotent since they commute. Then whichever power whatever's the biggest power you need to raise to get each of them being 0. Actually no. So the nilpotency degree of this will be the sum of the nilpotency degrees of this guy and this guy. But you need that they commute to see that. We've used that before. Okay, so now we've got a semi-simple matrix and a nilpotent matrix, but the only matrix which is both diagonalizable and nilpotent. Nilpotent means all its eigenvalues are 0. It's also diagonalizable, so it must be equal to 0. And so xs equals xs prime and xn equals xn prime, and that's the uniqueness. Okay, so what about existence? Well, we can just pick a basis. So x is in Jordan normal form. So it's just got some Jordan blocks. Down the diagonal, I am trying to draw Jordan blocks, but I'm not very good at it. There we go. And now you just take xs to be the kind of diagonal part, and xn to be the upper triangular part, just the ones in the Jordan normal form, right? So this would be in this one. So it's just take the lambdas and the mu's down the diagonal. That's xs. And for xn, just take the ones up above in the Jordan normal form. These clearly commute. They sum to x. xs is diagonal. And xn is nilpotent. So we've got all the properties 1 through 4, but we haven't got the final part. We need to know that xs is some polynomial in x and xn is some polynomial in x. And we needed that for the proof of uniqueness, right? I needed that final part exactly in my uniqueness proof. So unfortunately, we're not quite done here. So to finish it off, let's let chi of t be the characteristic polynomial. Of this endomorphism x, right? So it's some product of linear factors t minus lambda I to the ni up to k maybe for some distinct eigenvalues, lambda 1 up to lambda k, right? So I'm over an algebraically closed field, so that's all good. If you let vi be the kernel of x minus lambda I times the identity to the ni, that's the generalized lambda I eigenspace of x. And then the v is just the direct sum of all of these generalized eigenspaces. Now what you do is you use the Chinese remainder theorem to show that there exists some polynomial p of t, so that p of t is congruent to lambda I modulo t minus lambda I to the ni for all I. Okay, so these different maximal powers of linear factors, these are all relatively prime, so you can solve that system of simultaneous congruences. That's Chinese remainder theorem. Now, think about p of x, this polynomial evaluated at x. On that generalized eigenspace, let me see, how do I say this? The polynomial x minus lambda I identity to the ni is 0 on vi, right? Because that's exactly its kernel. That's the definition of that generalized eigenspace. So that means this polynomial restricted down to vi, x evaluated there is just 0, so the polynomial just evaluates to lambda I times the identity on vi. So p of x is exactly xs as I wanted. Oh, but I need p to have constant term 0. So I've actually got to throw in one more congruence in my Chinese remainder theorem. I want that p of t is congruent to 0 mod t, so the constant term of p is 0. That was also a requirement, right? And there's absolutely no harm imposing this extra one if 0 was an eigenvalue. This doesn't contradict the earlier congruence required. That's for free, and that forces this constant term to be 0, and then finally you let q of t be t minus p of t. And then xn, the nilpotent part, is just the q of x, right? So that finishes the proof. Okay, so that's a fundamental piece of linear algebra, this Jordan decomposition in endomorphisms of a finite dimensional vector space. So any endomorphism decomposes into its as a sum of its semi-simple part and its nilpotent part. They're semi-simple and nilpotent, and they commute, and that those properties determine xs and xn uniquely. Okay, so just a little bit more discussion to try and kind of explain where we're going with this in the next couple of lectures. If you have a linear Lie algebra, and you have an element x in G, then by the Jordan decomposition you have xs and xn, the semi-simple and the nilpotent parts of that endomorphism of V. But do they actually lie in the subspace G? Right, so if G is just some linear Lie algebra, you can any element of G is an endomorphism of V, and you can apply this Jordan decomposition. It has these unique semi-simple and nilpotent parts, which will just be some more endomorphisms of V. It would be very nice if the semi-simple and nilpotent parts actually lay in the subalgebra that we were studying. And the answer is, of course, not in general. Just think about G being one-dimensional subalgebra. There's no reason. So it's very easy to see that's certainly not going to be true. But we'll show it is true if G is a semi-simple Lie algebra. So that's going to be a very important structural feature of semi-simple Lie algebras. Somehow this Jordan decomposition for endomorphisms of a vector space, you can upgrade it to get a Jordan decomposition for any semi-simple linear Lie algebra. I mean, I guess I could do one little example right away, right? If it happened that G was SLN, that's a linear Lie algebra because it lives inside GLN. And in this case, if you have x in G, you can write it as xs plus xn. It's semi-simple and nilpotent parts, which will be in the whole of GLN. But of course, x has trace 0 because it's in SLN, and xn is nilpotent. So all its eigenvalues are 0, so xn has trace 0. And those things together imply that xs has trace 0. So in fact, xn and xs do both lie in SLN of C in this case. So this silly argument works. In this case. But it's kind of cheating, isn't it? What if G was like SON or SP2N or something like that? Do the semi-simple and nilpotent parts of a matrix X in that classical Lie algebra, do they necessarily lie in SON or SP2N? So we're going to show it, but it's so totally not obvious at this point. Given that they do, so this thing we're going to prove for semi-simple Lie algebras in a little bit, what happens if you have some other representation. From G to some other GL V prime, with V prime being finite dimensional. I mean, is it true that if you take some element of G and look at its semi-simple part, which we'll show for semi-simple G belongs back to G again, and then you apply this representation to it, is that the same as the semi-simple part of the matrix rho of X, the endomorphism of V prime? Or is it the same for nilpotent, right? Does taking the semi-simple or nilpotent parts commute with representations? Again, we'll show this is true for semi-simple Lie algebras, of course. But it's going to take quite a bit of work this week, and so that's sort of kind of where we're heading. But let me just give you one more example of a special case. What if G happens to be GLN of C, and you take rho to be the adjoint representation? So I'm looking at add from GLN to the general linear Lie algebra GL of G. Proving these two properties, because of the uniqueness part of Jordan decomposition, actually it boils down using uniqueness to prove that rho of a semi-simple is semi-simple, and rho of a nilpotent endomorphism of V is a nilpotent endomorphism of V prime. That's what it's really all about. If you have a semi-simple element of G and you apply a representation to some other GLV prime, does it stay semi-simple? Or if you apply rho to something nilpotent, does it stay nilpotent? And in this case, if X in G is nilpotent, we already know that add X is nilpotent too. That was something we needed when we were proving Engel's theorem. Maybe you remember how it went. The point was that add X looked like left multiplication by X minus right multiplication by X. These were both nilpotent and they commute, and so therefore that difference is nilpotent as well. And the same goes for semi-simple. If X in this GLN is semi-simple, so diagonalizable, it's also true that add X is semi-simple. So let me just quickly finish by explaining that. There's not a whole lot going on. You may as well assume that X is just diagonal. And then the way add X acts on the IJ matrix unit, this is a super important calculation. It acts as the scalar Ti minus Tj on the matrix unit. Therefore, add X is diagonal in the basis of matrix units. So that exactly shows that the adjoint representation of GLN sends nilpotent matrices to nilpotent endomorphisms of G, and it sends semi-simple matrices to semi-simple endomorphisms of G. So that's kind of a little baby special case of something we're going to have to prove much more generally for semi-simple Lie algebras as we go.